We may have to sort of hit the high points, but I guess that's true anytime you're trying to review everything in civil engineering in 10 weeks. Are y'all all three taking the exam in April?
I think just I am. Mm-hmm. She's taking the FE.
Okay.
I'm going to try to take the metal mechanical one later, but this is still a good review for that too.
Oh, okay.
Does she have?
It's also directly applicable to my job.
Okay, well, great.
Now did they say they're taking FE?
She is.
Only one person taking.
If you got a good FE review book?
Yes, I do.
Okay.
It's pretty good.
All right, because I got some of those laying around too.
Okay. Well, we're flipping over here to engineering hydrology, and each of these are major topics in which we'll just spend a little bit of time on each of several major topics, and looking first at subsurface flow, and then stream flow routing, flood frequency analysis, precipitation runoff modeling, and then reservoir yield as time allows. So going underground first, and this is to get us thinking about the water underground, and just basic terms defined here. We've got an aquifer, and we've got a confined aquifer, meaning there's a confining layer above it as well as below it. We've got an unconfined aquifer, and so if you drill a well in an unconfined aquifer, the water table is going to be where the water rises in the well. If you drill a well into a confined aquifer, the water will rise all the way to the piezometric surface, and so this would be equivalent to the hydraulic grade line. This is analogous to pipe flow, and pipe flow where you've got your piezometric surface and groundwater flow, you'd have your hydraulic grade and pipe flow. And well, moving on, and flow through porous media, we do have particles, the soil particles through which the water is flowing. We can take just a few minutes to talk about the basic definitions and the basic concepts that are pertinent in the various types of analyses. And the aquifer parameters, porosity is very important. The volume of the voids divided by the total volume. And so the water is just in the volume in between in the voids in between the solid particles there. The volume of voids divided by the total volume is porosity, and then the hydraulic conductivity, some people call that the coefficient of permeability. That's the flow rate through a unit area under a unit hydraulic gradient. And another way of expressing the same concept is transmissivity, and instead of being a flow rate through a unit area, transmissivity is a flow rate through a unit width under the same unit energy gradient, or hydraulic gradient. Energy gradient and hydraulic gradient means the same thing. And so if we're talking about permeability, if you just take a unit area, 1 foot by 1 foot, or 1 meter by 1 meter, or whatever, we're just talking about the water that's flowing through that unit area, and what makes the water flow through the porous media is a change in the water table or piezometric surface, the slope of the water table or the slope of the piezometric surface. Now, if you want to, and that would be in gallons per minute through that square foot, or whatever the units, cubic meters per minute through that square meter of area. If you want to express that in terms of transmissivity, transmissivity would be the flow rate through this through this unit width. And so again, this would be if it's an aquifer we're looking at, this would be the top and this would be the bottom, and then the flow rate through that unit width would be the transmissivity. And so the transmissivity is just the vertical depth of the aquifer times the coefficient of permeability, the hydraulic conductivity. This table just has some typical numbers in it. Clay, for example, clay has a very high porosity, And so on first glance you might think, that would really be a good aquifer because it holds lots of water. But because clay particles are so small, the water can't escape from the clay. And so here, Pacific yield is the volume of the water that will drain freely under the force of gravity. And with a 3% Pacific yield, there's almost none of the water will drain out of the clay. And the coefficient of permeability would be in gallons per day per foot squared would be 0.01 gallons per day per foot squared, or in meters per day 0.0004. Now, most aquifers for which municipalities get water supply are sand and gravel aquifers. Now, the porosity is lower than clay, for example, but the water will drain out of it. The permeability is high, as well as porosity being high. When we talk about Darcy's law in just a moment, it will be pertinent to differentiate between actual velocity and apparent velocity. And so water is flowing through the porous media, and the water is just flowing through the void spaces. The solid particles are blocking the flow. And so we have, if we think in terms of the discharge rate, if you took the total area and thought in terms of the flow through this total area that we're looking at here, the apparent velocity is discharge divided by area. And so if you took the total flow through this porous media and divided it by the total area here, that would be a little q, which is called an apparent velocity. It's a Darcy velocity. Now, the actual velocity is actually greater because the water is not really flowing through the total area. It's just flowing between the particles. And so if you take the actual velocity is the q divided by the actual area through which the water is flowing, and the actual area is the total area divided by multiplied by the porosity. And so the actual velocity is the apparent velocity divided by the porosity. The porosity is the volume of the voids divided by the total volume. That's true, but that's also a representation of the area of the voids divided by the total area. The basic equation for flow through porous media is Darcy's law, and it says that the flow rate is equal to some constant of proportionality, and what this constant is, it's the coefficient of permeability. That's a flow rate per unit area per unit hydraulic gradient. So if you take the K, the permeability, the flow rate per unit area per unit hydraulic gradient, and multiply it by the area, and then multiply it by the hydraulic gradient, you get the flow. And so A is the area through which the water is flowing, and then the hydraulic gradient, that's just the head upstream minus the head downstream divided by the length. And so if we let the hydraulic gradient be J, it's just KAJ, and instead of a total flow rate, if we use the little q, flow rate per unit area, it would just be KJ. And this is a little experimental apparatus that illustrates the concept. If we've got water coming in here, we've got a sample of sand, we've got a supply of water, the water flows through the sample, and then it discharges out the bottom, and we want the flow rate through. A is a cross-sectional area through there, and then if we inserted a piezometer here, we'd have the head upstream of the sand. A piezometer here would give us the head downstream of the sand, and the flow rate would be proportional to that difference in head divided by the length through which the water is flowing, and then it would be also proportional to the area through which the water is flowing. Here's an example just to illustrate an application of Darcy's law. And here we've got a discharge of 70 gallons per minute being pumped from a well in a sandy aquifer. 2 observation wells located at a radial line 250 feet. So this well in the middle is the one being pumped, and then these other 2 wells, we're just making observations of water levels. And so one of them is 250 feet from the pump well, and the other one's on the same radial line 325 feet away. So there's 50 feet in between those two observation wells. And so what's happening is you're pumping water out of this well. What you've got coming in is in all directions through the aquifer, the water's flowing toward the well. And so the water's flowing in toward the well. Now we need some way to estimate the hydraulic gradient. And the problem set that up for us because it's taken these two wells and made measurements of the water table, the elevation of the water surface there. And let's see, it says that there's a 1 foot difference in water surface, and they're 50 feet apart, so we divide 1 foot by 50 feet, we've got the hydraulic gradient, the slope of the water table, and that'll give us that information. And then we need the area through which the water's flowing. And so this is a plane view. We're looking on this from an airplane looking down, and so the depth of the aquifer is given, and it's given as 80 feet. So if you look vertical from the paper, from the water table down to the bottom, the aquifer is 80 feet in depth, and so we're flowing in all directions toward the well through this 80-foot vertical distance. And so we can plug into Darcy's law, and actually what it asks us for is the hydraulic conductivity and the transmissivity. And so the K in Darcy's law is the hydraulic conductivity, and the information given will provide all the other terms. Let's see, the flow rate is given, it's in gallons per minute. We need to convert units to cubic feet per day, so we'll have consistent units when we combine everything. So 70 gallons per minute, and going through these conversion factors will convert that to 13,476 cubic feet per day. The flow area we're going to need to plug in the A in Darcy's law, and you need to visualize, use your imagination just a bit, and visualize the area through which the water is flowing when it has that gradient. So we're putting, we know the gradient between these two wells, so we're letting the circle go through the two wells, and it's so the circumference of the circle times the depth. Circumference of the circle is 2 pi times 300 feet times the depth, which is 80 feet. And so that's the area through which the water is flowing as it flows in this way toward that pumped well.
And how do you get to 300 feet?
I need to know the gradient. I need to plug in both the area and the hydraulic gradient. And so I need the area at the same place I have the hydraulic gradient. And the way I know the hydraulic gradient is at these observation wells over here, I know the water level in the wells. So that tells me the water surface. So I'm using, there's a difference in water elevation of 1 foot between these two wells, so I'm saying that's an approximation for the hydraulic gradient halfway in between them. And so I'll just use the area halfway in between them.
All right.
And then we're plugging numbers in, and at that distance out from the well, I know the hydraulic radius. The H1 minus H2 is 1 foot, and I've got the 50 feet. I need the area at the same distance away. I plug that in. I know the flow rate. I know everything except K, so I solve for K. And that's coefficient of permeability, the hydraulic conductivity, and it's actually in cubic feet per day per square foot of area. But the cubic feet divided by square feet cancel out, and so you often express it just in feet per day. Now the transmissivity is the same thing, except instead of being the flow through a unit area, it's a flow through a unit width. And so we multiply the hydraulic conductivity of 4.47 feet per day times the vertical height of the aquifer through which the water is flowing of 80 feet to get that the transmissivity is 358 cubic feet per day per foot of width. And here's a second example to same basic law, Darcy's law. a second set of numbers to plug into Darcy's Law in a little different context. We've got a confined aquifer, and it's 2.4 miles wide and 65 feet thick. So vertically, there's a confining layer on top, a confining layer on bottom, and so that vertical distance is 65 feet, and then going into the paper, it goes 2.4 miles into the paper. And so we approximated the vertical and the horizontal width through which the water is flowing. And it's flowing from a recharge zone toward these wells. And the difference in the water surface elevation in the two wells is 7.2 feet. So we measure the water surface, the difference is 7.2 feet, so we know also the horizontal distance between the wells, so that gives us the hydraulic gradient. And we want to compute the discharge through the aquifer, and we're given the hydraulic conductivity in this problem. The K is 0.035 feet per second using that particular set of units. And of course that's cubic feet per second per square foot of area. And we also want to compute the travel time, how long it takes water to get from here to the observation well here, and that's 6 miles. Okay, plug into Darcy's Law again. This time this time we know the hydraulic conductivity. This time, like the last time, we know the hydraulic radius, hydraulic gradient. So H1 minus H2. Well, the area, we need to compute the area, and the water is flowing from a river or from a recharge zone where there's rain falling on the recharge zone. And so the flow area into the paper was 2.4 miles. The vertical distance was 65 miles, and we got to have a unit. 2.4 miles and 65 feet. So we need a unit conversion of 5,200 feet per mile, and so that's the total area through which the water is flowing, the 823,680 square feet. So we plug that in for A. The hydraulic conductivity is given, and that's in cubic feet per second per square foot, which reduces to feet per second. Plug that in. The difference in the elevation of the water surface in the well, two wells is 7.2 feet. They're 800 feet apart. That gives us a slope, a gradient, and we know everything except the discharge, so we solve for the discharge. Now the velocity of the water. The second part of the problem is how long does it take the water to travel the 6 miles that it's traveling between those 2 points. And so we take the total flow rate and divide it by the area. A velocity is a discharge divided by the area. We get 0.000315, but that's just an apparent velocity. That's not the actual velocity. If we went back to the previous page in the notes, we'd have to divide it by the porosity to get the actual velocity. And so the actual velocity is 0.0009 feet per second. Time is, so the water is actually flowing between the particles through the void spaces at that velocity. Time is length divided by velocity. It's traveling 6 miles at 0.0009 feet per second, and so it's going to take 9,780 hours to get there, to travel the 6 miles. And that's a quick overview of one concept. That's Darcy's Law, which is a very fundamental basic concept for flow-through porous media. And having said that, unless you've got questions or comments, we're going to jump on to another topic.
This sounds pretty easy.
Okay. We're going back to stream flow, and this is related back to the open channel hydraulics. So this is normally considered hydrology, the actual routing. And what the topic now is hydrologic routing, and the basic concept is you got water coming into something, you want to compute the water going out. Now a simple case is you've got a reservoir. If it's a drainage, urban stormwater management problem, you've got a stormwater detention basin. If you're on a major reservoir, it's a major reservoir in a river. Doesn't matter how big the reservoir is. Basically, you've got water coming in and water going out, and routing is given the inflow hydrograph. A hydrograph is just a discharge versus time. Compute the outflow hydrograph. And this is very fundamental, very basic to designing detention basins, designing reservoirs, and so forth. Now, we can also do routing in channel reaches, and that's given the water coming into a reach of channel, what's the outflow at the downstream end. Given that so much water is being released from the gate in a dam, how much water the flow rates 5-10 miles downstream. The basic concept is very straightforward. It's the continuity equation for unsteady flow is expressed here. Inflow minus outflow is a change in storage with respect to time. And that's true whether it's a bucket with a hole in the bottom of it in which you're trying to fill up the bucket and water's coming in the top and running out the hole in the bottom, or if it's a reservoir, or it's a reach of a river, or whatever. Inflow minus outflow is change in storage with respect to time. Delta derivative storage with respect to time. Now we can approximate we can write this in a finite difference form and say that the average inflow minus average outflow is equal to the change in storage with respect to time. So here we're using subscripts 1 and 2 to denote the beginning and ending of a time period. Inflow at the beginning of the period plus the inflow at the end of the period divided by 2 is an average inflow during the time period. And likewise, outflow at the beginning plus outflow at the end divided by 2 is an average outflow. And the difference in the average outflow and the average inflow is the storage at the end of the time period minus storage at the beginning divided by the time period delta t. And so what we're dealing with here, a hydrograph is discharge versus time. So we plotted an inflow hydrograph. That's a hydrograph coming into the flow rates coming into your stormwater detention basin. Now, the purpose of the stormwater detention basin, or the flood retarding structure, is to attenuate the hydrograph, to reduce the peaks. And so this is the hydrograph coming out, and routing deals with computing this hydrograph coming out. And so we'll step through time, some delta t at a time, and each time we'll know the inflow at the different points in time. We will have just computed O1, and the task will be to compute O2. Now, all of the hydrologic routing methods are based upon this continuity equation. There's some different methods. We'll look at 2, one for reservoir routing, one for routing in a reach of a river, and the difference is based upon this thought. This is one equation, but there's going to be 2 unknowns. O2 is an unknown, S2 is an unknown. We'll know all the inflows. We'll have just computed the outflow, and we will have just computed the storage at the beginning of the period, but we will not know the storage at the end of the period, nor the outflow at the end of the period. So we need some other relationship between storage and outflow. And that other relationship between storage and outflow is what makes for different routing techniques. Now, modified poles routing, this is an old technique that's been around for a long time. This is in all of the computer models that you use to do drainage design, deal with urban stormwater management, reservoirs, and so forth. But poles came up with it, I think, if I remember the original paper, 1928 or such. And I'm not sure how it got modified, but we call it modified poles or the storage indication method. So the basic concept is here. You take your continuity equation, put everything you know on one side of the equal sign, the things you don't know on the other side of the equal sign. We don't know S2, the storage at the end of the period, nor do we know the outflow rate at the end of the period. So this expression's on the right-hand side. We'll know values for all of these variables. We can plug them in. We want to call this something. That expression can be called the storage indication, the 2S over delta T plus the outflow. And so what we do, we compute this term step by step, and having computed that term, what we really want to know is the outflow, so there's got to be a relationship between 2S over delta T plus the outflow. And so we've got to have a relationship between outflow and 2S over delta T plus outflow. And to get that relationship, you've got to have a relationship between elevation of the water surface versus outflow and elevation versus storage. Now for a reservoir, that data is readily available because elevation versus outflow comes from the hydraulics of outlet structures. Weir equations and orifice equations express discharge as a function of head above the crest of the weir, which is spillway, and overflow spillway would be a weir, or the head above the center line of an orifice, which a conduit to a dam would be an orifice, and you can develop that relationship. And then elevation versus storage comes from a topographic map. If you have a contour map of a reservoir site, whether it's the largest dam on the Mississippi River or a small detention basin in the middle of a city, with a topographic map for any given elevation, you can compute the storage volume behind the dam. Now, if you develop that relationship, we've got a couple of examples. In the first example, I've already developed the relationship. In the second example, we develop it as part of the problem. And so if you've got a relationship between outflow and 2S over delta T plus outflow, then you can simply use the continuity equation to route an inflow hydrograph through. And let's say we want to design a detention basin so that the 50-year recurrence interval flood can be, someone's developed a shopping center, maybe Fort Hood's done some work in which they've paved over some ground, and in the city of Killeen, I guess Killeen's downstream of Fort Hood, but doesn't want to get any worse drainage problems than they had before, so you're designing the detention basin so that the 50-year flood before your development is no worse for Killeen than the 50-year flood after the development. And so a basic concept there would be to route the 50-year flood through. Now, if you design a detention basin for your particular design with your outlet structures and the topography of the site is represented by this curve. And then you take your hydrograph, and we'll talk about exceedance probabilities and flood hydrographs in just a moment. But here we've got the inflow hydrograph, whether it's a 50-year design storm or whatever. For our purposes at this moment, it's a given inflow hydrograph, and we want to compute the outflow hydrograph. And so the modified poles routing computations, the basic continuity equation, and so we plug into the continuity equation. And so I've set up some columns to keep track of the numbers. We're stepping through time. And so at time 0, there's no inflow, so it's reasonable assumption that there's 0 outflow. And from our curve, 0 outflow means that the storage indication is 0, and so we've got zeros at the beginning. And so we just plug in the numbers. And the first thing is I1 plus I2. At the very first time step, 1 means the first line of information, 2 means the second, before the end and the beginning of this 1 hour delta T. And so we say 0 plus 30 is 30, I1 plus I2, and then we've got a 2S1 over delta T minus O1 of 0, which we add in, and we get 2S2 over delta T plus O2 of 30. And since these are subscripts 2, I'll put it on the line which I've designated the end of the time period. Then we take the 30 to the graph of the previous page and read out a 5. And so at 1 hour after time 0, we got 30 cubic feet per second coming into the reservoir. We got 5 cubic feet per second leaving it with outlet structures. Now to do it all over again, we're going to need a 2S over delta T minus outflow, and that comes from this expression. If 2S over delta T plus outflow is 30, and the difference between this term minus outflow and the same term plus outflow is just 2 times outflow, as I've expressed here. And so if you just take 30 minus 2 times 5, you get 20. And then you just plug into the equation again. We got to change the subscripts. This is the second hour, so this is the beginning of the second hour, subscript 1, the end of the second hour, subscript 2, So I1 plus I2, 30 plus 60 is 90. We just computed the 20, add the 20 to the 90 to get 110, and then from the 110 we go to the curve to get 18 cubic feet per second coming out, and then we do it all over again. And so, given the inflow hydrograph, we've computed the corresponding outflow hydrograph, where all of the site characteristics, the topography of the detention basin site or reservoir site, plus the outlet structure characteristics are incorporated in that storage indication curve. Notice that we do have attenuation. The peak inflow is 180 cubic feet per second. The peak outflow is 65 cubic feet per second, occurring sometime later. So we have attenuated the peak on that hydrograph, and that's the purpose of the reservoir, is to attenuate the peak, to decrease the discharge by temporarily storing water. This second problem, same type of a problem, except we got to develop the storage indication curve. And so we've got elevation versus storage and discharge data for the reservoir given. And so we have to have a topographic map to get, if we've got a topographic map for any given elevation from computing volumes using contour intervals and planimetering the area enclosed within contours, we can get the storage. The storage volume below any given elevation. And then doing the hydraulics of the outlet structures for any given elevation, we can get outflow. And then this is S, storage, that's O, outflow. So, and we're using a computational time interval. When we flip to the next page, we'll find that our inflow hydrograph is spaced at intervals of 12 hours apart, the discharge ordinance. And so we've got a delta T of 12 hours, and by doing unit conversions, we can say 2S over delta T, plus outflow is computed directly from those numbers, delta T of 12 hours and the proper unit conversions, and then we've got a relationship between outflow and 2S over delta T plus outflow, which I've plotted up here. And then knowing that relationship, it's the same problem as before. Given the inflow hydrograph, we plug into the continuity equation. and so inflow hydrographs given, I1 plus I2. First time step is 12 hours for a delta T. Subscript 1, the beginning. Subscript 2, the end. We've got to come up with an initial condition. And in the original problem statement, it said the reservoir water surface is at 875 feet above mean sea level at time 0. So at that elevation, the 2S over delta T plus outflow is 1010. The outflow is 0, and so 1010 minus 2 times 0 is 1010 for the 2S over delta T minus outflow. And then we plug into the equation repetitively. I1 plus I2, 40 plus 35 is 75, plus 1010 is 1085. We go to the storage indication curve of the previous page to get the 0. And then subtract 2 times 0 from that to get the 2S over delta T minus outflow, and repeat the computations. And so given the inflow hydrograph, again, we've computed the outflow hydrograph. And I've gone over that very quickly. Usually in some of the courses we cover this in, we'd probably spend an hour and a half on this. And so, but I'm hoping you got the basic concept there. One of the things you really need to do for the exam is going to be to work some problems yourself, because we're going over some things, but to really be able to work problems, you need to work problems, so be sure to work through some of the problems. And there's lots of examples in the reference material, of course, that you've got. Okay, questions, comments about modified pulse? Just basic
We
content.
said the same thing to each other. We got to work the problems to find out if we got it.
Yeah, you do. You're going to have to work problems yourself, and to really get prepared for an exam, where the exam is working problem. That's a very fundamental technique we just went through. It's widely used in many applications in designing different types of storage facilities. And it works very well for reservoirs because reservoirs have control structures. They have spillways and outlet structures so that there is a well-defined relationship between the storage and the reservoir and the outflow through the outlet structures. Another problem, though, is routing through a river. In a river reach, you don't really have a well-defined control structure. It's the frictional resistance of the river all along the reach that's holding the water back. And you get a phenomenon called a looped rating curve, which is illustrated here. And what this curve says, for example, if you were sitting on the bank of a river, and let me draw a river in right up here in the corner. Here's an upstream, this is just a river, the water's flowing downstream, and maybe there's a dam here, you're making releases to generate hydroelectric power, or maybe there's a precipitation event, you're doing some flood control drainage work, and for a given rainfall for a design storm, you got some flood hydrograph here, and you want to compute the flood hydrograph downstream. Well, what happens to you is that one way of visualizing this, pretending that you're sitting on the bank of the creek watching the river rise, and the river's rising, and at some point you note the elevation, there's some discharge rate, and for that discharge rate there's a certain amount of water in storage up here. Now it keeps on rising, finally it peaks out, and so the river's gotten as high as it's going to get at that point, and it starts falling. Now as it falls, you finally get to a point where you got exactly the same discharge rate as you had back a few hours ago that I noted. Same discharge rate, but you've got much less water in storage, because what's happened to you is the flood wave has come through, and when the river was rising, even though you had a certain discharge here, the peak of the flood wave was upstream. You had a lot of water stored in the river upstream. But then after the peak goes on downstream, you might have the same discharge here on the falling side of the flood wave, but most of the water's downstream now. And so saying what I just said again, you've got a loop rating curve in that for some given value of storage, let's do it this way, some given value of outflow, you could have different values of storage in that reach. And so there's not a unique relationship between the outflow from the reach and the amount of water in storage in the reach. And so if you think about it, if you can't relate storage simply to outflow, like you can when you've got a concrete spillway and outlet structure in a reservoir, what can you relate the storage to? What's a logical thing to relate storage to? Well, how about inflow and outflow? And Muskingum, you're saying that storage is a function of both inflow and outflow. So that's the function, and I guess we've got that on the next page of notes. But what we're doing in the Muskingum routing method, and this is a common routing method for river routing, it's certainly not the only method. There's other alternative approaches. This is a widely used approach, though, and it's in all the textbooks and all reference manuals, and is widely used in practice as well. You take the continuity equation, the same continuity equation that we worked with before, but then you say storage is a weighed function of both inflow and outflow. And so the simplest function would be to just weigh inflow and outflow. So X is a weighing factor between 0 and 1. And so if X is, say, 0.2, then 1 minus X is 0.8. So it's taking the inflow times 0.2 and the outflow times 0.8. It's weighing both the inflow and outflow. And typically X is around 0.2. It's usually a weighing factor by definition is a number between 0 and 1. It's got to be 0.5 or less, or you would not be attenuating. You would be getting a peak discharge downstream bigger than the peak discharge upstream, which you cannot have. And it's been found it's usually around 0.1, 0.2, 0.3, 0.2 is a typical value. And so if you take this expression for storage and plug it in there with a subscript 2, and then take the same expression with subscript 1 for the outflow and the inflow and plug it in there and algebraically manipulate, you get this Muskingum routing equation. And so that's the Muskingum routing equation. And so the parameters are the value x and a k. And this k is a representation of travel time through the reach. It has units of time. And so this is just one equation you're looking at. It's just the outflow from the reach of river at the end of the time period is equal to some C naught, which is this expression, which is a function of k and x and the delta t, plus C1, which is this expression, which is also just a function of delta x, or xk and delta t, plus C2 times the outflow at the beginning of the period. And just to check arithmetic, C0, C1, and C2 always have to sum up to 1. And so that's a routing equation that's commonly used in rivers. And the routing is fairly straightforward if you know x and k. And so we've got an example in which we're given an inflow hydrograph at an upstream location, and we've given the routing parameters, the x and k for the river reach, and we want to compute the downstream hydrograph. And so this is plugging the numbers into the equation. And so given x and k, and on the next page when we look at our upstream inflow hydrograph, we're going to see that the ordinates are 6 hours apart, and so delta t is 6 hours. So we just plug in the numbers into the equation from the previous page, and we'll get a C0, a C1, and a C2. Those numbers will add up to 1 like they're supposed to. And so we take those and we plug them into the routing equation. This is called a coefficient method because it's just taking the inflow at the beginning and end of the period and the previously computed outflow and multiplying them by constants. And so O2 is just the C0 we computed times I2 plus the C1 we computed times I1 plus the C2 we computed times O1. So I've got a typo, so we need to fix that. Subscript 2 here should be subscript 1. Everybody fix that?
Yeah.
Now, at time 0, we'll assume steady flow at the beginning. If there's 10 cubic meters per second upstream, we'll assume 10 cubic meters per second downstream, and then it's just a plug-in. And so subscript 2 is the end of the period, so to get the inflow hydrographs given, so to get the outflow, we just take I2, which is 30 times 0.125, plus 10 times 0.52 plus 10 times 0.523, and we get 12.4. Then we do it all over again. And when we do it all over again, the 6 hours, that's subscript 1, and the 12 hours, that's subscript 2, the beginning and ending of the second 6-hour increment of time. And so we say 68 times 0.125 plus 30 times 0.352 plus 0.523 times 12.4 to get 25.5. And we route through, given the hydrograph coming into the river reach at some location upstream, we compute the hydrograph at some location downstream. Okay. We're changing topics. By the way, all these topics are related. For example, I gave the practical application that's widely used of delineating 100-year floodplains in cities to regulate development. And that's applied throughout the country in all cities. To do that, you've got to work with a 100-year exceedance frequency design storm, do rainfall runoff modeling, the next topic, and then you've got to route it through the system using the routing technique we've just talked about to get discharges throughout the system, and then you take those discharges and plug it into the standard step method solution of the energy equation to get the water surface profiles throughout the river system. And so the topics are related, but we are going through a number of different topics here. And so, on the topic of flood frequencies, we can define exceedance probability. Exceedance probability is the probability that a flood of a specified magnitude will be equaled or exceeded, and we almost always use a year as a time period. And then recurrence interval is the average interval in years between occurrence of a flood of a specified magnitude or an equal or larger flood. So one's a reciprocal of the other. Recurrence interval is the reciprocal of exceedance probability and vice versa. And so we're talking about, we're designing a bridge to cross a river. Our standards are to design the bridge so that there's we use the term a 100-year flood, that the 100-year flood will go under the bridge but not over the bridge. And so in any given year, there'll be a 1% probability that that discharge will be equaled or exceeded. Or if you're designing your culvert, maybe for a 25-year flood, that means that in any given year, there's a 4% probability that that design discharge will be equaled or exceeded, and your culvert capacity will be equaled or exceeded. And so we design bridges and culverts and inlets to storm sewer systems, and we design storage capacity and detention basins and all types of structures and management strategies. We delineate 100-year floodplains to keep people from building houses too near the river. All of these things we do for a given exceedance probability that's specified in the criteria we're using. Now, another formula that's quite useful, if you think in terms of exceedance probability, let me write the symbol. It's the symbol P. P is the probability that a given event will be equal or exceeded in any given year. 1 minus P is the probability that that event will not be equal or exceeded in any given year. If you assume the event statistically independent, like flooding, we assume the occurrence of a flood in any given year doesn't affect the probability of the flood occurring the next year. Then 1 minus P to the n is the probability that the event, that flood will not occur in any series of n years. And then 1 minus P to the n would be the probability that that given magnitude flood will be equal or exceeded in any series of n years. And we call that the risk. And so that's the risk formula. And using the risk formula, in this example, what's the probability that the 100-year peak discharge excuse me, at a certain location on a river will be equal or exceeded in the next 100 years? We're using the risk formula. We need the exceedance probability. The exceedance probability is 1 over the recurrence interval. 1 over 100 is 0.01. So plug in 0.01 for the exceedance probability. We're looking at a series of 100 years, and so there's a 0.34% probability that the 100-year discharge will be equal or exceeded in the next 100 years. Okay, a lot of people would argue that we shouldn't use the term recurrence interval because we have a major flood event, and the Corps of Engineers makes an estimate that the 100-year flood just occurred, and the newspapers published this was a 100-year flood, and all these people are flooded, and they've been told it's a 100-year flood that just flooded you, and then they reason, well, if I just got flooded out of my house by a 100-year flood, well, the 100-year flood's not going to come again until the next 100 years, and I'm probably won't be alive in 100 years anyway, so I'll just move back in, and just like everything's going to be fine for another 100 years. So I understand there's a regulation within the Corps of Engineers now that in public releases, instead of using the term recurrence interval, we use the term exceedance probability to make sure everyone understands that there's a probability, regardless of what flood you had this year, there's a probability that it's going to be equal or exceeded again next year and the year after that. And for example, what's the probability of the 100-year flood being exceeded in the next 20 years? Well, there's an 18.2% probability that the 100-year flood will be exceeded in any period of 20 years. And so if you design your bridge to pass a 100-year flood, you got an 18.2% probability that it's going to be overtopped in the next 20 years. And you can plug in the numbers to show that. Plug in the 0.01 for P, plug in 20 years for N, and you'll get a risk of 0.182. Doing the same thing again, we've got a temporary cofferdam being sized based upon a 25-year design storm to protect a construction project which will take 5 years to complete. What's the risk of the cofferdam being overtopped during the 5-year construction period? So convert the the recurrence interval to an exceedance probability 0.04, plug it into the risk formula to get whatever that comes out to be. And that, I guess, comes out to be 0.185. So, given an annual exceedance probability, we can get the risk of a given discharge being equal or exceeded in any other period other than 1 year, 5 years, 20 years, whatever. But we've got to use data to actually get the exceedance probabilities. And so there's different ways of doing that. And a viable plotting position formula is just the concept of relative frequency. And the plotting position formula is given here, where M is a rank, N is the number of years of data, or we can use a probability distribution function. And the two widely used probability distribution functions for extreme events are the extreme value type 1, which I've given here, or the log Pearson. Well, I've given here an equation form, and it's often used in equation form, or log Pearson type 3 is used for flood events, flood discharges as well, and it's given in this form. And so we'll refer back to this page in just a moment. Probability distribution functions have parameters to calibrate the model to the real-world data, and so those parameters are the mean, the standard deviation, and the skew coefficient. And so most calculators will have the mean and the standard deviation. Many will not have the skew coefficient built into the functions in the calculator. Okay, here's a set of numbers, and just using these numbers we can illustrate, go back to the previous page and look at the techniques for estimating probabilities. And so what I've got here is a string gauging station. I'd like to have 30, 40, 50, 60 years of data, but that would make for too long of a sheet of paper for my notes, so we're just using 15 years of data. And so I've taken an annual series, and what I've got is for each year of the record, of the 15 years of the record, I've got the peak discharge occurring that year. And I've ranked them in descending order. And so for the 15 years, the highest value occurred 575. That was the peak for 1968. The second was 419. And the smallest, 1973, the maximum discharge in 1973 at this location was 206 cubic feet per second. So what we want to do is take this data, use the data to estimate probabilities for any given discharge. One way of doing it is that viable plotting position formula. And so you've got that page in front of you, and I do too. I don't think I'll switch it on the screen here, but notice it says that the exceedance probability is the rank divided by the number of years of data N plus 1. And another way of writing it is the recurrence interval. It's just the reciprocal of the exceedance probability. So we say the recurrence interval is the number of years of data, N, which in our case N is 15 years. We've got 15 years of data. M's the rank. And for the rank, we just start with number 1. So the biggest number, the 575 cubic feet per second, has a rank of 1. So the second biggest, a rank of 2. The third biggest, a rank of 3. You'll notice this example problem is somewhat cluttered because I've worked several parts all on the same sheet. We're doing the analysis using the alternative methods. So I'm just using this column. These are the rank. We rank the numbers. And Well, if you just thought about it, just looked at those numbers and forgot everything that I've said and forgot everything you've seen in the notes other than just this column of numbers, and I picked out a number and I said, this number, 387, what's the probability in any given year that the peak discharge will equal or exceed 387? And what would be just sort of a logical answer to that? If you think about it, how many, you had 15 years, right? And in those 15 years, the peak discharge equaled or exceeded 387 cubic feet per second 3 times, so 3 out of 15. And so whatever 3 divided by 15 is. What is that, 0.2? And so that's just the concept of relative frequency. The problem with that is, if I ask the question, what's the probability that the peak discharge will equal or exceed 206 cubic feet per second? In the 15 years, every year it equaled or exceeded 206 cubic feet per second. So we'd say 15 divided by 15 is 100% probability. But we all know there's not 100% probability of equaling or exceeding 206 cubic feet per second. There's a non-zero probability of value less than that. But the same concept is embedded within this plotting position formula. What I've just suggested in my comments is divide M by N, but to prevent ever getting 100%, we can divide the rank M by the number of years of data, N plus 1, and then we'll never get 100%. And so that's the basic concept there. But using the plotting position formulas, we can compute recurrence intervals, and then we can plot recurrence interval versus peak discharge, and I've actually plotted them here on probability paper, draw a line through that, and use that to assign probabilities for any given value of the discharge. Exceedance probabilities or recurrence intervals. The problem with that is that the biggest recurrence interval we got is 16 years, and in many design applications we want to design the hydraulic structure for a 50-year recurrence interval or 100-year recurrence interval, and there's no way you can extrapolate. It would be very approximate to extrapolate. And so what we normally do is we fit the data to probability distribution functions. I've got, the example actually shows 2 probability distribution functions, but maybe to save time we can look at one of them. And so we look at the Gumbel extreme value distribution, and all this does is a relationship between values that the random variable x takes on and the corresponding exceedance probability. And so the 2 parameters are the mean and the standard deviation. And so from those 15 years of data, we've got to compute a mean and a standard deviation. And so having computed the mean and standard deviation, I can plug them in at the appropriate places. And then if I wanted to compute the discharge corresponding to a 10-year flood event, let's say a 10-year recurrence interval, that's an exceedance probability, 1 over 10, 0.1. I can plug in the 0.1, and then I can compute the B here. And so I'm just going through the arithmetic of computing the B. Once I've got the B, I plug it in, and then I plug in the mean, the standard deviation. The only thing I have left is an X, and I solve for X. And so given that 15 years of data, assuming that the Gumbel probability distribution fits stream flow data, the 10-year recurrence interval peak discharge would be 431 cubic feet per second, just by using the Gumbel. Now, if I wanted the 100-year recurrence interval, what I could do is just plug the same numbers in. The exceedance probability would be 0.01, plug in 0.01, compute the B, and again, it's all just one equation. We just write it in 2 components to make it easier to write out. So having computed the B, that exponent being 4.6, plug in the standard deviation, plug in the mean, and compute an X of 608 cubic feet per second. So again, I've just taken the data, and used the data, reduced it down to 2 parameters, a mean and a standard deviation, and then used my probability distribution function, a probabilistic model of the peak annual flows to assign a exceedance probability or a recurrence interval to any given flow. Another way of doing the same thing would be the log-Pearson type 3 distribution. It's a little more complicated. I think I'm tempted, just because I'm looking at the clock, to skip over that and move on to another topic. That was talking about discharges. We can also talk about rainfall. And rainfall runoff modeling is necessary in a lot of design work because we have no stream gauges. The only way you can do a frequency analysis for gauge stream flow data is to have a stream gauging station. But if you're doing drainage work, if you're designing highway culverts and storm drain inlets and storm sewer pipes and detention basins and bridges and those kinds of things, you're not going to have a gauging station where you need a gauging station. So what you're going to have to do is work with rainfall data and do rainfall runoff modeling. And we often use design storms, and well, here's some rainfall data. This is the city of Houston, and cities will have this type of information which they provide in their drainage criteria manuals. I've never checked at Fort Hood. I would assume Fort Hood has a drainage criteria manual that's used to size all of the drainage facilities on the base. But anyway, for the city of Houston, this is rainfall intensity in inches per hour versus duration, and it's for a given recurrence interval. So we've got a 2-year recurrence interval is represented by this line, a 5-year recurrence interval up to a 100-year recurrence interval. What you're looking at is a very typical way of expressing the IDF relationship, the relationship between rainfall intensity, duration of the rainfall, and the recurrence interval. I notice in the reference manual they express it different ways, and I think in the examples they do it different ways. Here's another way of expressing the same relationship. This is the way the Texas Department of Transportation does it. And so when you're doing design work in the Texas Department of Transportation, you use this equation, and the same equation is used in other states as well. This is a very common way of expressing an intensity duration frequency curve. And so B, D, and E are regression coefficients, and the Highway Department has provided those in a table. And for example, the A&M watershed model has all of the coefficients coded into the computer software package. But they're a function of location and a function of recurrence interval. So for a given, the way the Highway Department does it in Texas, they've got the table set up for every county in Texas. So you pick your county, there's 254 counties, that gives you a location. Then you pick your recurrence interval that you're designing something for, and then that'll give you a B, D, and E. And once you plug those in, you've got a relationship between intensity in inches per hour and duration of the rainfall. And I gave some numbers because we're going to do some examples in just a bit. And for a 50-year recurrence interval in Brazos County, that's where we live here in College Station, the B, D, and E are these numbers, so we plug them in, and that's our IDF relationship. For a given rainfall duration, for a 50-year recurrence interval, we can compute the mean intensity in inches per hour. And I'll need that in just a few minutes. We need to do rainfall runoff modeling, and this is just to transition us to that. And this is the process. We're going to use some simplified approaches, but basically we need stream flow data because we need to design a drainage facility, or we need to design a reservoir, or we need to delineate a floodplain. So we need stream flow data, but we don't have gauge stream flow data, but we've got precipitation data. Either gauge precipitation data or IDF relationships like on the we just talked about. And physically what happens now, precipitation falls, you got lots of hydrologic abstractions, interception, depression storage, you replenish soil moisture, a lot of that evaporates, infiltration, you get some overland flow, you get some interflow as the water flows in the impervious topsoil. We call that direct runoff. And so this is a representation to remind us that there are some complex physical processes happening in the watershed which we are trying to represent, and we do it in simplified ways in the rational method and the unit hydrograph approach, which we're about to describe. The rational method is widely used for 100 years now. It's been widely used in drainage design in particular. It's widely criticized because of its simplicity, and it's widely used because of its simplicity. And so the basic equations given here, the peak discharge is CIA. And so what you want to do, you want to know what discharge do you design your culvert for, your inlet to your storm sewer, the size of storm sewer pipes, all these different parts of a drainage system or a stormwater management system, what discharges. Now this technique is valid for very small watersheds. And there's rules of thumb about when the watershed's too big. Basically, the smaller the watershed, the more valid the method. Some people use the rule of thumb of 100 acres. They'll say the watershed's 100 acres or less, you use the rational method. If it's more than 100 acres, you go to another method, most often the unit hydrograph, which we'll look at next. Some people use a square mile as a drainage area. The ideal situation would be a drainage inlet in the middle of an airfield. In the middle of an airfield where you know what the watershed area is, and the runoff coefficient's close to 1, but a highly pervious concrete asphalt small watersheds for drainage inlets would be the ideal application of the rational method. But it's used to size culverts and so forth. So the peak discharge and whatever unit you want to use, engineers in the U.S. So often will use what they'll do, they'll plug in a rainfall intensity in inches per hour, a watershed area in acres, and then they'll call the Q sub P cubic feet per second. And that comes out if you recognize that 1 acre inch per hour equals 1.0083, which is very close to 1 cubic foot per second. But essentially, it is a dimensionally correct, consistent equation that you can use any dimensions in. The C is a dimensionless runoff coefficient, and I is an average rainfall intensity, and it's for a duration equal to the watershed time of concentration, the T sub C. And the A is a drainage area. And so if you sort of visualize, they call it the rational method because the concept is it's not theoretical, it's sort of rational. You can reason out that this would be what would happen. And the concept is this. Assume a uniform rainfall is falling over the watershed. And so it rains for 5 minutes. At the end of 5 minutes, all of the water that fell on this line has had time to get to there. So we say this part of the watershed is contributing. Now, it keeps on raining. Now, at the end of 10 minutes, and what this line represents is a distance of 10 minutes the way the water flows. So it takes water 10 minutes to get from here to here, to the outlet. The outlet's the inlet to your storm sewer system. Now, so that amount of the watershed's contributing. Maybe in 20 minutes, it takes water 20 minutes to get from there to there. Now, if it rains long enough, the entire watershed's contributing. So we assume the peak occurs when the entire watershed's contributing. Now, when the entire watershed's contributing, we assume if it keeps on raining at a constant intensity, you're in an equilibrium condition. What's falling on the watershed is running off of the watershed. Inflows equal to outflow. Now, if we go back to the IDF curves, we showed the IDF curves for Houston. And what happens is, for a given recurrence interval, for a longer duration of time, the corresponding mean intensity is going to be less than for a shorter duration of time. And so the longer we make the duration for a given recurrence interval, the less is going to be the mean intensity. And so what we want to do is what we just argued here, we want it to rain at least long enough for the entire watershed to contribute. So the basic procedure that's been used for decades is you set the rainfall duration equal to the time of concentration of the watershed. And then you assume you got an equilibrium of what's falling down is coming off, except everything's not coming off the watershed because some of the rainfall is lost through infiltration and the other hydrologic abstractions. So the C is a dimensionless number that tells you what's coming off of. That's just the proportion of the rainfall that actually runs off of the watershed. The rest of it's lost through infiltration, etc. The concept is fairly simplified, but it is a widely used concept, and I would anticipate this method would have a high probability of showing up on a fundamentals of engineering exam because it is widely used and it is simple enough that you can sit down with a pencil and calculator and get a peak discharge to design something for. Unique coefficients, the C is an empirical coefficient. I Xeroxed this out of the engineering reference manual, which you have. And so they've just given for different types of land use and different types of surfaces some typical values for the runoff coefficient. And you can look at those in your manual at your leisure. We want to illustrate the rational method by using an example problem. I've got a parking lot, and this works good for parking lots because they're small watersheds, and it's in College Station, and the dimensions are given. And you can see the dimensions of the parking lot, and I've got a gutter running right down the middle. And so what's happening, the rain falls on the parking lot, it drains off to the gutter collects the flow, and it puts it into this storm inlet. And we want to design the storm inlet, so we want to know the discharge that we got to design the storm inlet for. And so some information's given. We're estimating that the flow velocity, the sheet velocity, is a half a foot per second coming across the pavement. And then once the water gets in the gutter, it flows at a velocity of 2 feet per second. And often we'll use Manning's equation to estimate a velocity in a channel, and there's empirical data about flows, sheet flows across pavements and across grass and other surfaces. We want to estimate the 50-year recurrence interval peak discharge. So we're going to design the storm sewer inlet for a 50-year peak discharge. Okay, so this is College Station. Notice College Station is in Brazos County, and we can use the Department of Transportation regression equation to get the rainfall data. Okay, so we need the time of concentration. And so travel time is just the length divided by velocity. And so the water is traveling across the pavement, and then it's traveling in the gutter. And so the overland flow time plus the gutter flow time will give us the total time of concentration. And so it flows 200 feet across the pavement at a velocity of a half a foot per second, and then the water flows 400 feet in the gutter at a velocity of 2 feet per second. And so it takes 10 minutes for water to get from the most hydraulically remote point in the watershed. And by definition now, the time of concentration is the time from the way the water flows from the most hydraulically remote point in the watershed, that corner, down to there, to the storm inlet. That's 10 minutes. I don't think I'll go back to the transparency, but you'll remember we used the Texas Department of Transportation regression coefficient for Brazos County, and we came up with this relationship where the rainfall intensity in inches per hour is the regression coefficient for 98, 8.5, and 0.74 for a 50-year recurrence interval. We'll plug in the 10 minutes for the duration of the rainfall, and we'll get a mean intensity of 11.15 inches per hour. So we've got the mean rainfall intensity. We need the watershed area. And if you look at your diagram, the parking lot is 400 foot by 400 foot. So that gives us a watershed area. We'll plug into this equation. I need to make an estimate for the runoff coefficient. Most of the water is going to run off. So I'm going to give it a number real close to 1. I'm going to be conservative. Let's see, in the Civil Engineering Reference Manual, I think they probably had numbers maybe 0.95. I'm going to be a little bit more conservative and use a 0.98. Plug in the numbers, I get 40.5 cubic feet per second. So that's the rational method. That's been an old workhorse for designing drainage facilities for small watersheds forever. That just gives us a peak discharge, peak flow rate. And so that works well for inlets and things that you design for peak flow rates. Now we're going to go to volume, though. We'll use this and the unit combine this with the unit hydrograph approach and use it for larger watersheds. There are a lot of different ways of computing volume, and the Civil Engineering Reference Manual presents this method, and this is a good choice because this is widely used, and it shows up in a lot of references. Almost all your hydrology books will cover the Soil Conservation Service. So this is the SCS Rainfall Runoff Model. SCS is Soil Conservation Service, and we're going to all have to learn to not say that anymore because several months ago I think they changed their name to the Natural Resource Conservation Service. But engineers have been saying SCS for enough decades now, it's going to take a while to get used to calling SCS methods Natural Resource Conservation Service methods. And so here's the equation, and we'll just basically present the equation and how to use it. We've got a runoff volume. This is the Q, and we're just using common convention here. The Q, which we've always used for a flow rate in cubic meters or cubic feet per second, is now a volume in inches. So we got to get used to the concept of a volume in inches. And so a precipitation volume in inches or runoff volume in inches, that's a volume equivalent to covering the watershed to a depth of that many inches. And so P is a precipitation volume in inches, Q is a the corresponding runoff volume in inches. And so a certain amount of precipitation falls on the watershed. If 10 inches of precipitation falls on the watershed, we're not going to get 10 inches of runoff volume. We're going to get less than 10 inches due to the infiltration and the other hydrologic abstractions. Now, point 2S represents the initial abstraction, and I'm not really taking time to derive this equation, but so anytime P is greater than 0.2S, that equation is valid. If the precipitation volume is less than the initial abstraction of 0.2S, then the runoff volume is 0 as well. So Q would be 0 anytime P is less than 0.2S. S, by definition, is called the potential maximum retention after runoff begins, and that's in inches. And the concept there, if it rains forever, what happens, the infiltration capacity decreases as the ground gets saturated, and the S is the maximum amount of infiltration you could have if it rained forever. That's what it physically represents. Now, to characterize a watershed, it's easy to work with a number between 0 and 100, and that's what the curve number is. So for convenience, the SCS defines a curve number like this. Typo, everybody be sure to fix this. S is 1,000. S is 1,000 divided by the curve number. I had 100 divided by the curve number. S is 1,000 divided by the curve number minus 10. And so we use the curve number to characterize the watershed. Now, if you had a curve number of 100, 1,000 divided by 100 minus 10 is 0. So a curve number of 100 means there's 0 potential retention. Everything runs off. But then as the curve number gets less than 100, if you go from concrete and asphalt down to a clay soil down to a sandy soil, and the curve number gets less and less, you get a greater retention of water through infiltration and other hydrologic abstractions and less runoff. So that's the basic equation. I've copied this out of the Civil Engineering Reference Manual, and this is just some runoff coefficients for different types of soil types, and they define the soil types in the book, but D would be like we have here in College Station, in which infiltration's at a minimum. That's clay soils. A would be sandy soils, where you have a high infiltration rate. And then, in addition to the soil type, the curve number is a function of the land use. And in your book, they do it for agricultural land uses. And in the notes, I also added another extension of this table, which is in many other references that show land uses for urban areas too, residential, commercial, industrial type land uses. And so you can estimate your curve number. And in the example here, we simply, we're running out of time, we'll go through this very quickly. We've got a 50-acre watershed in Brazos County. We got a curve number estimated to be 86. We want to compute the direct runoff volume to result from a design storm with a recurrence interval of 50 years and duration of 24 hours. We use the Department of Transportation regression equation with the coefficients which we've used already. We plug in 24 hours in minutes. That's 1,440 minutes. We get a precipitation volume of 10.4 inches. We plug into the SCS curve number, a rainfall runoff relationship to get a resulting runoff volume of 8.7 inches. That's used in the unit hydrograph. We've got about 5 minutes here, and so we're going to normally, I teach a graduate class in open channel hydraulics, but I also teach a graduate class in surface water hydrology, and we would spend several hours on the unit hydrograph, but I think somehow we're going to do it in 5 minutes here. And so the basic concept is this. In the unit hydrograph now, this is for large, complex watersheds. The rational method is a simplified approach for a small watershed. The unit hydrograph gives you not only the peak discharge, but the entire hydrograph for larger watersheds. And so the concept is that for a given watershed, that you can ratio the ordinance of the hydrograph in proportion to direct runoff volume. For example, here's a hydrograph, discharge versus time. And it has a runoff volume is represented by the area under the curve. And so a unit hydrograph has a runoff volume of 1 inch. And so let's say that we have a rainfall event. In the previous example, we had what, 10 inches of, we had 10.4 inches of rainfall, and that gave us a runoff volume of 8.7 inches. So the concept of the unit hydrograph is that all you would have to do is take a unit hydrograph and multiply it by 8.7 inches to get the runoff hydrograph that corresponds to a 8.7 inch direct runoff volume rainfall event. Now, when you apply a unit hydrograph, you got to develop rainfall data. We've done some developing of rainfall data. You got to compute the rainfall excess, the direct runoff volume, using a technique like the SCS unit, the SCS rainfall runoff relationship, which we just did. You've got to develop a unit hydrograph, and then you take the unit hydrograph, the direct runoff volumes, and you apply the unit hydrograph. And so we've got a couple of examples that'll finish us up here. And the first example, we'll develop a unit hydrograph, and then having the unit hydrograph, we'll apply it to a design storm rainfall event. And so there are different ways of developing a unit hydrograph. Well, we don't have time to cover all of them. The Civil Engineering Reference Manual talks about some different ways. The ideal way would be if you had a stream gauging station and you had stream flow data to develop it from. And that's what this example is doing. In this example, we're given this hydrograph. And given this hydrograph, we want to compute a unit hydrograph. And so what we do is fairly simple. These are the ordnance. These are the discharges at different points in time for the given hydrograph. And so all we're doing is ratioing the ordnance. And so we numerically integrate the hydrograph. That's just finding the area under the curve. And so one way of finding the area under the curve, and if I just add up these ordnance, and they add up to 61,500, and what I'm doing, and then multiply that by the 2-hour time increment. In other words, what I'm doing is just taking this hydrograph and just taking these little rectangles, like so, and with these rectangles getting the area under the curve. And then I'm doing a lot of conversion factors. And after you do all the unit conversions, it comes out to 3.18 inches. And so this given hydrograph has a direct runoff volume of 3.18 inches. Right there. So you divide each of those ordnance by 3.18 inches, and you get these ordnance. And that's what we've done in this column. So these ordnance represents a hydrograph that has a direct runoff volume of 1 inch. And the important thing that we need to note is that the original hydrograph was created by a rainfall event with a rainfall duration of 2 hours. And so this is a unit hydrograph for a 2-hour duration rainfall event. And now we'll finish up by applying that unit hydrograph. And so we're saying the example watershed is in Brazos County, Texas. We got a composite curve number of 80. We've got design. We're going to develop a design storm, and we're going to compute the runoff hydrograph for the design storm using the computational interval of 2 hours. So maybe we need to size for urban stormwater management. We want to size a detention basin. And we're going to develop a design storm, a 50-year recurrence interval hydrograph to size our detention basin based upon. And so we're putting together several different things here. First thing we need to do is develop rainfall data. And so if you'll just focus on the first set of computations, what we've done, we're using a 6-hour rainfall duration. We've got a unit hydrograph for a 2-hour rainfall duration, and so we're going to compute rainfall volumes for a 50-year recurrence interval design storm using a 2-hour time step. And so we're using the Department of Transportation equation, which we've used already, and we're saying if it rains for 2 hours, that's 120 minutes. We plug into this, and we get 2.63 inches per hour, if it rained for 2 hours. Now, if you multiply 2.63 inches per hour times 2 hours, you get 5.26 inches, if it rained for 2 hours. Now, if it rains for 4 hours, you're going to get more rain, and so we plug 240 minutes in, that's 1.61 inches per hour, times 4 hours is that total volume of rainfall. Now, if it rains for 6 hours, we'd get that total volume of rainfall. And this is a way the Corps of Engineers uses this quite a bit. The Hydrologic Engineering Center in the HEC1 flood hydrograph package includes this technique, and this is sort of a conventional Corps of Engineers technique that's been used by everybody else as well to develop a design storm. So rainfall, the duration of a design storm is somewhat arbitrary. We're using 6 hours, somewhat in excess of the time of concentration of the watershed. Now, if it rains for 2 hours, you're going to get 5.2 inches of rain. So we're going to put that right in the middle, and then if it rains for 2 additional hours, you're going to pick up an additional 1.18 inches, and we'll put that there. And if it rains for 2 more hours, you're going to pick up an additional 0.76 inches, and we'll put that there. So we'll put the most intense 2 hours in the middle and less intense on either side. That's called a balanced triangular rainfall distribution. A lot of textbooks will call that an alternating block rainfall distribution. There are other ways of doing rainfall distributions. So in our hypothetically, computationally created 50-year recurrence interval design storm, that's how much it rains in each 2-hour increment of time. The unit hydrograph applies to direct runoff volume. So we use the Soil Conservation Service equation that we looked at previously, and we take cumulative precipitation volumes and compute the corresponding cumulative runoff volumes, and then take the increments of runoff volumes, and then we take each of those increments. For the first 2 hours, we're saying we've got 1.18 inches of rainfall. It results in a runoff volume of 0.15 inches. And then we ratio the unit hydrograph ordinance in proportion to that to get a resulting hydrograph. Second 2 hours, we got that volume. We ratio unit hydrograph ordinance to get a discharge hydrograph. Third 2-hour increment of rain, we've got that direct runoff volume. We take each time, we take the unit hydrograph that we computed in the previous example, we ratio ordinance in proportion to the direct runoff volume, and then each 2-hour increment of rain began 2 hours later, so we lag everything by 2 hours, and then we add them across to get the runoff volume. Now, that set of computations, within the Corps of Engineers, there's computer software packages. There's a package called MILHY, the Military Hydrology Model. By the way, have y'all ever used or had contact with the Military Hydrology Model? The Military Hydrology Model does those computations in the computer software just the way we've done them. And then the Civil Works program, the Hydrologic Engineering programs, HEC1, does those types of computations. And it normally takes a couple, 3 weeks, several lectures to go through that. We've gone through it very quickly, I realize. But we are over time, and you've been listening to me a long time, so I think I'll stop talking, and I'll be glad to answer any questions or discuss anything you want to go over again, or any points of discussion at all. We've covered a lot of material, I realize that.
We just want to say it was clear as mud.
Yeah, if you understand everything that we've covered tonight, just from listening to me, you've done something no one else has ever done. And so hopefully we've gone over it, and you can maybe go through the reference manual. And the key, I think, to doing well on the exam is going to be to work a lot of problems yourself. If we have
Ralph, there on the last example you just did, and you have the 3 columns with the 0.15 and the 4.03 and the 0.7.
Right.
What do we multiply? I don't see where those numbers are coming from underneath it. I mean, what?
Okay. The numbers that you just cited, those are direct runoff volumes corresponding to time increments of rainfall. So what we did,
Right.
we took the unit hydrograph. In the previous example, we developed a unit hydrograph. So we took
Right.
the unit hydrograph, and we multiplied the unit hydrograph ordinance by those numbers. And then we added them all together. Well, I understand you have new chairs tonight. Did that make 3 hours of sitting any easier? They're red. Last week they were a different color.
These are a lot softer.
Okay.
My brain's not as cramped. What have we been sitting there? Those? Regular ones? All right.
They're warmer, too.
We need some of those down here. This room really gets cold around 9 o'clock. I tell you, it's chilly.
I tell you.
Well,
I've nothing but air traveling underneath it.
Well, I've enjoyed it. Next week there'll be, I think, Calvin Woods will be back talking about sanitary engineering, wastewater treatment, and related topics. Right.
Well, winter.
Okay, we'll see you guys.
Field.
See you guys then.
All right.
Okay.